All right, today is our second day working with circles, and we're going to apply some various formulas here dealing with arcs, sectors, and chords. So let's first get some definitions down. The first one that we want to recall, even though you probably remember this already, is the circumference. We're going to be dealing with that a lot today. And that's just the perimeter of the circle, that outer edge. If we have an arc, it's just going to be a portion of that. We'll see an image of that later in our notes. A sector is going to be the area made by connecting the arc to the radius. That's going to look like the pie slice or a pizza pie slice in our circle. And the last thing we're going to deal with is a chord. This is just going to be a line segment that connects the circumference. So starts on the circumference, ends on the circumference. It does not need to be the radius or diameter. So first off, dealing with arc length, here's a visual of what the arc looks like. And this arc length is going to be this length here, like the crust of our pizza or the crust of our pie. Okay, so that's what an arc looks like. And since it's only going around a fraction of our circle, it is just going to be kind of derived from a fraction of the circle itself. So let's think back. Our circumference formula is 2 times pi times r right here. So if we wanted to calculate the entire perimeter, we go 2 times pi times r. So if we want to find the formula for this in degrees, if we wanted to find the arc length in degrees, we would use that 2 times pi times r, 2 pi r. But in front of that, we would multiply by a fraction of whatever our angle is, divided by, and that's that theta sign, divided by 360 degrees, right? Because our full circle is 360, and partway through that circle is our rotated angle. Let me just update that theta so it's nice and clean. Okay, and similarly, our radians formula can be the same thing. All we got to do is switch that fraction up. So instead of over a full rotation of 360, if we're rotating in radians, the full rotation would be over 2 pi. So times that 2 pi r. What's really convenient about this one and really nice, and I want you to kind of add this on and box it, is that the 2 and the 2 cancel out, the pi and the pi cancel out. So really all we need to do if we're given the radian measure is just go angle times radius. Let's practice this on some example problems. So example 1 through 4, we're going to find the length of each arc. We're going to round our answer to the nearest tenth. So we have a radius here of 11, an angle of 315. So if I'm setting up my formula, I'm going to have my length is going to be 315 over 360. And I'm just going to multiply that by 2 times pi times that 11. And we should just go straight to Desmos with this. We have it set up. Let's go to Desmos. So we go 315 over 360, and I'm going to multiply by 2 times pi times that 11. That gives me an arc length of 60.5 if I round that. So 60.5, and feet is the unit of measure on that problem. So that's our answer there. Then for problem 2, kind of same setup. We have a radius of 13. We have an angle of 270. I'll kind of do this on the side so it stays separate from my other one. So my length, the length of this full arc all the way around, is going to be some fraction of the full length. So it's going to be 270 over 360 times 2 times pi times that radius of 13. And again, this looks like we have feet as our measurement. So I'm just going to go in, I'm going to update my numbers in Desmos. So I can swap out that 315 for a 270. The 2 pi is there, and that radius is 13. So we get 61.3 feet. Okay, similarly, we can do this with our radian measures. Notice how example 3, example 4 have our radian measures here. So I recommend using that simplified version in this case. I'm going to work it through the second or both ways on the first one just so you can see it. But let's start by setting it up with that simplified version, just taking that angle and multiplying it by r. So if we have this problem here where we're trying to find the arc length, then our angle is just 3 pi over 2, and we can just go times 16 And if I throw that into our Desmos calculator, we go 3 pi over 2 times 16. We just get 75.4, and this will be feet as our units of measure. However, I'm going to also kind of throw in, on a side note here, what that full formula would have been, because I want a reminder that it's based on our fraction. So if we'd have 3 pi over 2 divided by 2 pi, so we have what looks like a really complicated equation here, but then we multiply it by, not an equal sign. That should be a multiplication. And we actually multiply it by that 2 times pi times 16. So what's happening there is that 2 cancels out on bottom, the pi cancels out on bottom, and we're just left with that radian measure times 16. So same thing will happen here for example 4. If we want to calculate that radian measure, we can just take that arc length, we can just take our radian measure of angle and multiply it by the radius 13. So if I type that into Desmos, we get pi over 6 times 13. Oh, and let me update that, pi over 6 times 13, so we get 6.81. Oh, and we want to round to the nearest tenth, so actually 6.8 is what we get here, and that is in inches. So moving on for sector area, the same thing can be done here because we're dealing with a slice of the pie instead. So this whole shaded region here, this is what a sector looks like. Similarly, it's a portion of our whole circle. So we're going to make it up we're going to kind of make up the equation as a fraction. So my equation in degrees for sector area is going to be based on this area of a full circle, that pi r squared. So my sector area S, if it's in degrees, we're going to take that theta, that rotation angle, we're going to divide it by 360, and then we're going to multiply by pi r squared. Radians will be the exact same thing. We take that angle theta, but this time we divide it by 2 pi because that's a full rotation. And here we have pi r squared again, so that shows up in both. In this case, though, if we simplify it, it's not as simple. All we can really do is cancel out those pi's. So if you want to use a more simplified version of it, you can go 1/2 times theta times that pi r squared. Up to you if you'd like to do that or not. So sector area, examples 5 through 8, calculating this one with degrees. So I have 60 degrees and 10 as my radius. So my sector area here is going to be equal to, let's set up that fraction. We go 60 over 360 times pi times 10 squared. And I'm actually going to set this second one up too before I go to my Desmos, so we can move through both of these pretty quick. My sector area here is 150 over 360 times pi times that radius of 3 squared. So I go back, let's do that calculation for the first one. I have 60 over 360 times pi times my radius is 10 to the second power. That gives me 52.4. And in this case, since we're finding area with inches, our units are going to be inches squared, 52.4 inches squared. The next one that we have set up, 150 times pi, 150 over 360 times pi, and our radius is 3. I'm going to throw that in there instead. We get 11.8. And this unit is in meters, so we have meters squared there. Working with radians, up to you whether you use the full red formula or that simplified green formula. It's probably easier actually to use the simplified green formula, at least to type it into Desmos. So I'm going to kind of teach it that way, but you can always go back and just use the full red one and simplify. So our radian formula here for sector area is going to be equal to that 1/2 times our angle, which our angle here is 3 pi over 2. And then we are multiplying it by pi. And I'm actually realizing that I made a mistake here. So let me kind of erase this and let's go back. And real quickly, we didn't screw up any of our examples, but let's go back up to our notes for sector area. The mistake that I made in here is that we actually have our pi's canceling out in this problem. So that simplified formula is actually going to be 1/2 times our angle times that r squared. We will not have that pi injected into it because it's canceled out by that other pi up top. Hopefully you caught that early on. And so let's apply that now to this formula here. We're finding the sector area. We have 1/2 times our angle measure, which is 3 pi over 2, times that 4 squared for our radius. And let's set up example 8 as well. Our sector area is going to be that 1/2 times our angle measure in radians, 17 pi over 12, times our radius squared. And now I can go ahead and just calculate both of those things. So I got the 1/2 times 3 pi over 2, 1/2 times 3 pi over 2, times whatever that radius squared is, which in this case is 4 to the second power. We get 37.9. Then our units there are centimeters squared. And on this next one, for example 8, we have 1/2 times that 17 pi over 12. And our radius measure is 14. So that's the number that's squared there, and we get 436.2. And that's in yards square. Okay, last thing we're going to learn today is dealing with chords. So we talked about chords, we defined it early on. All that is a line going across our circle. So this is what a chord is, this is what a chord is. We could draw another chord here, that's a chord, that's a chord, that's a chord. We have a bunch of instances of chords that we can draw. It's basically a line going across our circle. Let me erase all that crap so we can kind of move on to what we're actually trying to deal with. If we're dealing with these intersecting chords, what we found, what mathematicians found a while ago, is that if I want to relate these together, we can multiply A and B together, and whatever those get, we are going to get C times D. So we can relate these intersecting chord lengths together with this small length A, multiplying that by the small length B, and then multiplying the small length C by that small length D. Okay, notice how they're paired together. The green line goes with the green, the blue line goes with the blue. I want us to actually ignore this example, so cross it out on your sheet here. And we can just go on to example 9 and apply this formula here. So if we have these intersecting chords here, it looks like I have some lengths 9 and 16 that I can multiply together. 9 times 16, and that's going to be equal to this 8 times x here. And so if I'm trying to find x, all I got to do is kind of work this out. That 9 times 16 is going to be 144. And that equals 8x. And then we can divide by 8 and get that our x value that would then equal 144 divided by 8, which is 18. Similarly, we could set this up where we have, on example 10, where we have a length of 10 times 18. So 10 times 18, that is going to be equal to whatever we get, x times 15. So 15 times x. If we go ahead and do that, 10 times 18 is 180. That equals 15x. And we can just divide by 15 on both sides to get what x is equal to. And in this case, x would be equal to, let's try this in Desmos, 180 divided by 15. It would be equal to 12.